Hello guys, my name is Abhijit and today we're going to look at Universal Logic Gates, which is session 3 of CSA or Computer System Architecture. So the objectives of this session is to familiarize with Universal Logic Gates and to understand the truth table and Boolean expression of Universal Logic Gates. So Universal Logic Gates, like if you know about electronics, or I'll just tell you if you don't know that logic gates are made up of semiconductors. Semiconductor is a type of material, like it's a category of elements that sort of conducts electricity. It doesn't fully conduct electricity, it doesn't fully block electricity, it sort of conducts electricity. It behaves differently to electricity, that's why we call them semiconductors. Like sometimes it passes, sometimes it doesn't passes, and with the adding of different materials it behaves differently. So that's how you make logic gates. And to make different type of logic gates we need different types of semiconductors. And when we are making a big, like a processor or a microchip, and we need different logic operations, we need AND, OR, NOT, NOR, XOR, XNOR, and we need different logic operations. And when we are using the actual logic case, like the actual AND, OR, NOT, and different types of logic case, we are using different types of materials. And when we are using different types of materials, what happens is it gets complicated to manufacture. Like think about, what should I say, mixing different types of material at a very microscopic level or a nanoscopic level. We are like, it's very complicated to manufacture different types of logic gates in a single, like it's very costly. That's the point. So the solution to this was to create a universal logic gate, and the universal logic gates are NAND gate and NOR gate. The thing about NAND and NOR gate is that they are self-sufficient. That means you can create all logic operations or logic circuits using just one of these gates. I mean, with combinations, like with different combinations of this same gate. So in that way, we only have to use a specific set of materials, and we just have to like arrange them in a specific set of ways. So that way we can reduce cost, reduce complexity of manufacturing, and manufacture loads of circuits or processors like in bulk at a low cost. So that's why we need universal logic gates. So that's what is said here. One of the main disadvantages of using the complete sets of AND, OR, and NOT gates is that to produce an equivalent logic gates or function we require two or more different types of logic gate. And NOT, or and NOT. Oh my god, when these words come together it's so confusing, right? And NOT, or and NOT. So funny. Okay, leave that. However, we can realize that all other Boolean functions and gates by using just one single type of universal logic gate, the NAND, NOT, and NAND is just an, like, it's inverse of AND gate. So we call it NAND gate or the NOT AND gate. It is not an AND gate. It is not AND gate. Or the NOR gate, which is the NOT OR gate. And it reduces the different types of logic gates required for a circuit, and that reduces the cost. That's what I explained a moment ago. The NAND and NOR gates are complements of the previous AND and NOR gates. That complement means inverse, like the opposite, and are individually a complete set of logic, as they can be used to implement any other Boolean function or gate. And as we can construct other logic switching functions use just these gates on their own, they are called minimal set of gates. And they are also commonly referred to as universal logic gates, and they are called self-sufficient gates because we can create all kinds of gates using them. So they are also called self-sufficient logic gates. So the NAND gate. So this is the circuit or the symbol for the NAND gate. A, B, and A dot B complement, which is equal to an AND gate, A B AND gate, followed by a NOT gate, which is also A dot B complement. A and B complement. And the NAND gate is a self-sufficient, can build any logic circuit with it, can be used to implement AND or not, and or not gate. And implementing an inverter using an AND gate. This is a circuit for implementing an inverter using the NAND gate. I'll draw it here. So when we are drawing circuits, first let's draw the AND gate, because we AND gate. So to draw the AND gate, we first have to know the truth table of AND gate, which is 0 0 0 1 0 0 0 1 0 and 1 1 1. This is A, this is B, this is A dot B. So you must be familiar with this. You have to study this by heart. You have to know that A dot B. What is A dot B? It is A and B. So to implement this using the NAND gate, let's draw a NAND gate. This is A, this is B. So what we get, the output as this is, we get A dot B complement, right? So we have to invert it to get A dot B. So we take it here, and to invert it, what we have to do is we have to take another NAND gate and we join both of its inputs and we connect it to the output of this NAND gate. So this is the NAND gate. This is also a NAND gate which functions as a NOT gate, because when we connect both the inputs together, it functions as a NOT gate. A NAND gate functions as a NOT gate. So here we got A dot B. So this is like the circuit diagram or the construction of AND gate using what was this? NAND gate. Sorry, I lost something there. I just wandered off. Okay, so this is how you construct a NAND gate using AND gate using NAND gate. Oh god, I'm so lost. So let me delete all this. Now back, new. So now let's construct the NOT gate, which I did before. This is A, this is A complement, and this is the NAND gate, which functions as a NOT gate. We connect both the inputs together and it functions as a NOT gate. Simple. And let me delete that as well. And now we need the OR gate. OR gate, I had a little trouble understanding this at first because I was trying to construct it on my own. So to construct the OR gate, we first need, so if you think about constructing the OR gate using diodes, we can see that we used two diodes and connected its output together and we got the output as an OR gate. So to implement that using a NAND gate, we have to think about like the closest thing we can get to a diode is a NOT gate. A NOT gate is a diode in invert. So if we connect both, if we take two NOT gates and connect its output together, and if we invert that output again, we can get an OR gate. So to construct a NOT gate, we just have to like join two inputs of a NAND gate, and now we have a NOT gate, and we draw one more one, and this is A, this is B, and we connect it together. So here we get, what do we get? A complement plus B complement, right? Which is A plus B whole complement, right? A complement plus B complement. So let me think. If 1 plus 0 equal to 1, 0 plus 1 equal to 1, 1 plus 1 equal to 1, a complement will be 0, 1 equal to 1, 1, 0 equal to 1, and no, a complement plus B complement is not equal to a plus B whole complement. But let me think. Let me attach a NOT gate here and let's see what happens. So here it will be, if this is 1, this is 0, here it will be 1, and here it will be 0. That's not right, right? Let's Google it. Okay. That's right. I got it. So we don't have to join them together. We just have to like, this is 1, this is 0, we get 1 here and 0 here. So what we have to do is, this is an inverted, so we just draw another NAND gate here and we connect them. So what happens is that when this is 1, this is 0, this is 0, this is 1, so we get 0, 1 here, so the output will be 0, and the output will be 1. If this is 0 and this is 1, we get 0 here, 1, the output still be 1. If both inputs are 1, both the inputs will be like 0, 0, the output will be 1 again. But if both inputs are 0, here it will both be 1 and the output will be 0. So this follows the truth table for OR gate. So you have to study this. Don't get confused like me, because I kind of get lost, but I would have figured it out myself, but I didn't have the time. I have to keep this video short, so that's why I googled it. Sorry for that, guys. So let me no. Now the NOR gate. The NOR gate is also self-sufficient. It can be used to implement AND or NOT gate, and to implement an inverter using NOR gate, you just have to solve the circuit, and it's the same thing. It's the same thing. I mean, for the NOT gate, it's the same thing. I'll draw that as well. Create a whiteboard. So we have, sorry for my drawing, guys, I'm not a good artist. Yeah, so this is A, this is B, and here the output will be A plus B for complement, right? Yes. So to implement the NOT gate, so if this is A, this is A dash, this is the NOT gate. So if here input is 1, the output is 0. If here input is 0, the output is 1. That's simple. So constructing the NOT gate using NAND gate and NOT gate will be very straightforward. There is no complication. Now let's construct the AND gate. So to construct the AND gate, let me think. If we have a NOT gate, so to construct the AND gate, let me think what can be done. We have a NOT gate, we have another NOT gate. If we have two NOT gates, the output will be just be inverted. That makes no sense. But if we do the same thing as we did with if we so here A, here B, here it will be A dash, here it will be B dash, and if we connect it to another OR gate, and what will happen? Here A dash, it will be A dash. If we provide 1 here, here it will be 0. If we provide 0 here, here will be 1. So here the output will be 0. If you provide 0 here, if you provide 1 here, the inverse thing will happen. Here 1, here 0. So here the output is 0. If both inputs are 0, both will be 1. The output will be if both inputs are 0, here the both input 1 and the output will be 0. So that's how we implement the AND gate. So that's how you implement an AND gate using NOR gate. So now let's draw the OR gate using the NOR gate. So that's very straightforward. We just draw an OR gate. This is A, this is B. So here it will be A plus B in the whole bar. So you just have to invert it again. So to do that, let's draw another NOR gate. Join its input together, connect it, and now we have A plus B. So it's simple as that, just straightforward, A, B and A plus B. So this is how you construct the AND gate, this is how you construct the OR gate, and this is how you construct the NOR gate using NOR or NOR gate. So this is the top view of a TTL 74LS family chip, and it says 74LS02 quad 2 input NOR gate IC package. So it has 4, quad means 4, 2 input NOR gates. That's it has total of I think 6, 7, 9, 10, 11, 12, 13, 14 pins. So in 14 pins, 2 pins will be VCC and ground, and the rest 12 pins will be the connections to the logic gates. So 12 divided by 3 equal to 4. So each logic gates have 3 connections, so that will be like 4. So that's an OR gate IC package. So let's now the XOR gate or the exclusive OR gate. This gate is like a bit, what should I say, fun to work with. This is the exclusive OR gate, and what this does is that it gives a true output when there is a difference in the inputs. Like if the inputs are same, the output will be 0. If the inputs are different, the output will be 1. You just have to remember this. The exclusive OR gate gives the output when there is a difference in the inputs. That is, if one of the inputs is 1, then only it gives 1 as an output. Otherwise, when the inputs are same, if both inputs are 0 and both inputs are 1, the output is 0. If both inputs are 1, both inputs are 0, the output is 0. So the exclusive OR gate is very simple. It's downright simple. Now things are going to get a little bit complicated. That is construction of the exclusive OR gate. Like using the complete set, using NOT gate, AND gate, and OR gate, we have to construct an exclusive OR gate. And this is the diagram. So let's do that. So let's try to construct that without looking. Yeah, let's construct the exclusive OR gate without looking. I don't know if I can do this, but the exclusive OR gate, the truth table is 0 0 0, I mean, yeah, 1 0 1 0 1 1 1 1 0. This is the truth table. So to achieve this, we need, what do we need? We can use an OR gate as an output if both inputs are, yeah, let's start with an OR gate. Let's start from the beginning. This is an OR gate, and we have 2 inputs for an OR gate, and this to these two inputs, let's connect. What should we connect? Think. Let's connect an AND gate, output of two AND gates. And if we connect, we need, if both inputs are same, the output should be 0. So to achieve that, what should we do? I'm not really sure. Let's draw two AND gates and see what happens. Oh no, just an AND gate. And now we have 4 inputs. Like, okay. So if now we have 4 inputs, and if one of the inputs is, if we need 2 inputs here, and let me connect them directly to one of the pins. So this is A, this is B, and let me see. If I invert one of the inputs, like, and connect them to each other, what will happen? If I invert A and connect it to B, then it won't work, I guess. And this to NOT gate, right? NOT gate. So if this is 1, it will go here, and if this is 0, here I will get 1, here I will get 1, here I will get 1, here I will get 1. Okay, cool. And here also I'll get 0. Okay, cool. If this is 0 and this is 1, here I'll get 0, 0, here I'll get 1, 1, and here also I'll get 1. Here I'll get 1, here I'll get 0. Cool. If both inputs are 0, what will happen? Here it will be 0, here also it will be 0, here it will be 1, and here it will be 0, 0. This is not an NOR gate. Oh, this is just an OR gate. Sorry guys, this is not an NOR gate. I mean NOR gate. And that's an OR gate, okay? Don't confuse it. That's an OR gate. And here I'll get 0, and if both inputs are 1, here 1 and here 0, here 1 and here 0, so here will be 0 and here will be 0. So yes, we have successfully constructed a, what was this gate? A XOR gate using AND, NOT, and OR gate. If this was a bit confusing to you, I'll do it again. I think now I have. So let's start with an OR gate, and let's connect two AND gates output to this OR gate, and let's connect these to A and B. Sorry, for this I'm going to say A and B, and I'm gonna invert this B input to an OR gate using an OR gate and connect here, and I'm gonna invert this input using an OR gate and connect here. So this way I will get an A exclusive B over here. So this is AND gate, this is AND gate, this is NOT gate, this is NOT gate, and this is an OR gate. So I think if you are not understanding how to construct this thing on your own, you have to by heart this, because this is also very important. It will probably come for the exam, because this is one of the very basic things that you have to learn, the construction of other logic gates using other logic gates. That's, yeah. And if you don't understand the basics of logic gates, things are gonna get very hectic. It gets tiring. You'll get confused, stressed out. You might even fall into depression. I don't know. Depends on you. So you have to put effort. You have to try to understand. You don't give up. Try your best. You can do it. Yeah. Like some people, like me, we like I've been working with logic circuits and electronics since I was in 6th grade. You may not believe this, but I actually understood this concept when I was in 6th grade because I was passionate about electronics, so I understand this stuff very easily. If you have confusions or if you have doubts, feel free to ask me. I'll help you with any way I can. I'll dedicate all my time for you guys because you guys are everything to me, and I'm also learning. I'm also revising things. I'm also spending time productive. I feel happy when I do this, and it affects my mental health because I'm doing something productive. I'm not overthinking, so it helps me. Thank you. And I think I have something more to cover. Let's see. The exclusive NOR gate, and that's also the opposite of the exclusive OR gate. You just have to add a NOT gate in front of the OR gate, right? Yeah, exclusive NOR gate. If both inputs are the same, the output is 1. So it's easy to construct. You just have to add a NOT gate in front of the OR gate. You don't really have to use the circuit. You can just use a NOT gate in front of the a NOT gate in front of here and achieve the same thing. It's the same thing. The exclusive NOR gate is the same thing. When both inputs are the same, the output is 1. When both inputs are different, the output is 0. That's it. And yeah, the output is 1 is obtained if both inputs are at same logic level. Either this is for the exclusive OR gate and this is for the exclusive NOR gate. Okay. So that's it for this video, guys. In this session, we studied about universal logic gates, NAND and NOR gate, and the exclusive OR gate and the exclusive NOR gate. So that's it for this video. This video is pretty long. Bear with me, study with me. You will get good marks. Thank you.